So another example, this is just another paper, a large number of sites were looked at, and generally what was observed that geogenic constituent or endogenous constituents showed this chemostatic response. So what does that mean? Two things, one good and one bad. So I like the bad things first. What it means is that we've created a persistent legacy source of these constituents in our watershed. So if we want to do restoration, if we are looking for, we need to think about both short-term and long-term impacts of restoration. If we are thinking of short-term impacts in terms of improving upstream water quality or Gulf of Mexico hypoxia, changing land use wouldn't do anything. What we need to do is more control at point, meaning creating wetlands that actually divert the water and treat it, or treating it near the Gulf. So there are different kinds of pollution abatement strategies which are more at where the pollution is occurring. So those are short-term measures that need to be taken. Of course, we don't want to transfer this legacy of contamination to the next generation. So then we need to focus on long-term measure, land use change, better use of fertilizers, because as I was showing in one of those, more than 40–50% of the nitrogen fertilizer that is applied to the soil is leached. So we haven't really figured out how best to use it. It's more so in the developing countries, but more and more research is done on that, and there are ways of exploring how we can reduce that leaching. So we need a balance of those two kinds of approaches. And if we want to understand impacts, we need to figure out how long it takes for a particular constituent to travel through the watershed. What is its reactivity within the watersheds? If we understand that, then we'll be good. The good thing for us modelers is that this is a pattern that we have found, and we can explore this pattern to develop these models across scales, to go from a single tile to upscale it to predict what is happening at the watershed outlet. So for example, if we have climate models that tell us how much the runoff is changing, we can use that to predict what the load is changing. Of course, it's not as easy as that. There are a couple more steps to it. For now, we've just found the pattern, and we are looking for ways to go from the pattern to the process and prediction stage. But this is where we are now. So I promised that I would come back to my last slide. So my title was Exploring Emergent Hydrologic and Biochemical Patterns in Catchments at Multiple Scales. So the linear LQ relationship is an emergent biogeochemical pattern. The tile-drained watersheds and the way it simplifies the hydrology is an emergent hydrologic pattern. So we are exploring that right now at multiple scales with the overall goal of developing robust but simple models, so that ultimately those can be coupled with socioeconomic models, which is what I would like to do in the future, to say what kind of farmer decisions are needed to be taken and what impacts you would see later. So with that, I would like to thank you again for being here. It was great coming here and giving this talk. Thank you. No, I do want to. So I've been, as I was saying, so most of my work that I've shown here is work that I was doing while doing my postdoc. So, and I just getting more into the groups over here, and eventually do want to go there. But we need to first figure out, to an extent, like this pattern and how that relates before going to that stage. Well, for the long term, you don't really want to be loading your system anyway. You want to also mitigate that and not have to, because wetlands also, so in Florida you see these examples of stormwater treatment areas, which are these wetlands that were created to reduce the loads. Well, what's happening now is that they have become overloaded, and so they are not working. They are becoming sources themselves, actually. So that's true for phosphorus, not that much for nitrogen. But so you need to be doing both. So water quality measurements are the data that I have shown is large scale data. So this is collected by USGS, and this I would say is about at the max you would get 8-10 data points a year. Well, sometimes more. So bi-weekly or monthly sampling is what they do. So the Little Vermilion data set, the Illinois watershed, that actually has hourly data. So it depends, and a lot of work, effort, money is now going into having these automated sensors. They are very expensive, but then you have this entire time profile and you understand a lot what's going on in these systems. But then you have this huge spatial extent that you need to figure out. So I would say the new automated systems do give you, so going out and collecting samples is one, you have to be very careful that it's not biased sampling, because a lot of times you don't go out when there is a storm. Graduate students do, they have to, but normally people don't. And so I would say in terms of accuracy, and if you have calibrated your sensor better, it is better. But a sensor, a nitrate sensor, just as an example, costs $15K. So how many of those do you put in your watershed, right? So what I believe in, honestly, is that you need both. So you need to integrate this kind of sampling, and there's more innovative samplers that are coming up, and I'm interested in I'm actually working on one of those, where these are more crude. So you put them and they give you the mass load per event. They're not like every minute or every hour, but then you get an idea of in space where your contaminants are coming from. So you need a mixture of all these. So the Illinois data set that we used right now to do the analysis was daily data. They collected 15-minute data, but we haven't processed that data set because it's just massive 10 years, 15-minute data set. We haven't processed that yet, so that's still there. But they did ISCO samplers. So ISCO samplers, you can set it to collect data at any interval that you want, and then you collect it over a storm period. So you have these bottles that collect samples every hour or 15 minutes, whatever resolution, and then you have somebody go out and pick them, change the bottles, and then you have another round. So that's the nitrate sensors are the most sophisticated, that second level of sophistication, and then you go with what's actually done most cases, that you go and take a sample during an event. Or so, so this one had the ISCO samplers.
Okay, that was for an event?
No, that was 10 years.
10 years?
Hourly data. That's what they have. Yeah, it's a very beautiful data set, and we've done a lot of other kinds of analysis with that data set. It's rare to find that good a data set.
So yes. What were you expecting to find before doing the analysis with like the how do you call that, chemostatic behavior? Yeah. You didn't have an idea what's going to happen? Or?
No, not really. What we were looking for is, well, what do the loads depend on? So it was pretty, so when you go looking for patterns, it's kind of difficult because you don't know exactly which you're searching for, but you're looking at these systems and you're looking for patterns. And I was describing this to a graduate student the other day, is that if you look too closely, you don't see the pattern because there's just some noise in natural system data. So you have to be looking at it a little bit far away to be seeing the pattern, kind of like those paintings where you need to be a little far to see the pattern. But at the same time, if you're too far apart, then you get into your own dream world and what you're seeing is not really true. So you have to play continuously this game of going a little bit away and looking for that pattern. So we didn't really search for any particular pattern. We said, what does the load depend on? Plot it against area, plot it against discharge, what are we? And we said, well, if we can somehow find any kind of relationship between load and discharge, that will be helpful. We were not necessarily expecting a linear relationship. We were definitely expecting more nonlinear, because if you look at local CQ patterns and hysteresis work that has been done based on that, we were expecting a nonlinear relationship. But this is the idea of emergent pattern, right? Some things that you see at the small scale, small spatial and temporal scale is not what emerges out of your system.
So, but that's the idea is if you have to discharge, you can predict the load?
Yes. If you have the discharge, and actually I've not shown that much here, if you have the discharge and if you know the land use, so the slope of that line, we found to be pretty well correlated with percent land under corn. Right? So if you have more land under corn, it's generating more nitrogen. So if this mean annual concentration is more. So if you know the land use, which you do, and if you know the discharge, which is relatively easier to predict than the contaminants, then you know the load.
Next year.
Right. So the thing that intrigued us and kind of made us think twice is if you think about these watersheds at these large scales, there's been quite a lot of conservation activities going on in terms of buffer strips, in terms of why aren't we seeing that signature here? And the answer is you would see that signature at the scale of a 10 kilometer square watershed where we are putting that. But at the large scale, for you to see that signature, it would take a relatively long period of time. So it's the time lag and it's the space and time that you have to play around with to be able to see that pattern. So if you have a riparian buffer, you would see something, but then maybe that signal is diluted because as you're going down gradient, there are other sources that are picked in. So it's a balancing game, and don't know really how that works, but ultimately all that doesn't change this, so which is what intrigued us, still intriguing us. Thank you.